Okay, good morning. I think we are going to start since we are going to be late as always. Okay, so today we have the pleasure of having with us Alberto Marín. Alberto Marín is an assistant professor of our department since July 25. Okay, he's a man of the house. Between 2014 and 2024, he carried out his Bachelor, his Master, and his Ph.D. with us here at UC3M. He got the Prize of Excellence for his doctorate. Okay, and Alberto has been involving in the kinetic plasma modeling for Hall effect thruster. Together with Enrique Bello, has been a main developer of fully kinetic code that is called PICASO, that now he continues to develop, partially by himself, but also together with some of the PhD students of the EP2 groups, like Guillermo and the two Mateos. Okay, his interest has been within this kinetic modeling in understanding some of the non-Maxwellian effects on the electron response in Hall thruster. This means aspects that cannot be studied with fluid models, like plasma wall interaction, collision schooling of plasma plumes, or anomalous transport. Okay, he has a research state at Princeton, at the Princeton Plasma Physics Labs, with Professor Félix Parra. Félix Parra is the head of theory of PPPL, and also is a former student of mine at Polytechnic University of Madrid. So Princeton is accessible to our students. Okay. Today he's going to talk us about of this plasma physics of Hall thruster that he has been investigating. Thank you, Alberto.
Thank you, Eduardo. Thank you for this very kind introduction. You almost said most of the introduction of this talk, so thank you for this. Well, I am Alberto. For those of you who don't know me, I have been working in Hall effect thrusters for most of my bachelor, for most of my PhD thesis, okay? And now I'm going to present some results, some of the latest results on the problems that we have been analyzing on Hall effect thruster, okay? So the outline of this presentation is going to be mainly this one, okay? I'm going to do a brief introduction of why we're interested in this problem, okay? Then I'm going to present the methodology that I'm going to be following, which is going to be called the particle in cell formulation. I'm going to be showing then some results that we obtain in different configurations, okay, which are well, aiming to tackle some of these problems that we will discuss. And then I will wrap up the talk with some conclusions and future work that lies ahead, okay? So without further ado, let's start. So why we are interested in space electric propulsion. Okay, as you know, electric propulsion offers a much higher specific impulse, so in principle it offers the possibility to have huge savings in mass as cost for the space missions. Okay, so in the last decade also electric propulsion has surpassed chemical propulsion for in space propulsion. Okay, it's important this in space because for launches, as you know, it doesn't work. Okay, it doesn't have enough thrust, but for in space propulsion it's a very good alternative to chemical propulsion. Okay, and here you have some examples, okay, of well, satellites and constellations of satellites that use this kind of propulsion. Okay, among all these all the technologies that we have for electric propulsion, we have plenty of them. Hall effect thruster is currently leading the leading technology for most commercial applications. And indeed, I think that all these applications that I have shown over here, all of them use Hall thruster. Okay, none of them use different technology. So now we have said that Hall effect thrusters are the leading technology. They have been working quite fine. So why do we keep studying Hall thrusters? Okay, if this is something that is working, why do we keep studying it? And the response of this is that the plasma discharge physics is very complex, and some of the aspects are not very well understood. Okay, there is a recent, or relatively recent paper in talking about these things, which gathers the main experts in this community. Okay, and they discuss different open problems in plasma physics. But the two main that are going to concern us today is plasma wall interaction and anomalous electron transport. Okay. So just to give you an overview of the Hall effect thruster, okay, here you have the typical performance figures of a classical Hall thruster, okay, in which you have an operating power of around 1 kilowatt, thrust of around 100 millinewtons, and specific impulse of 1500 seconds, efficiency between 50 and 60%, and a lifetime of 10,000 hours. Okay. After that, due to erosion, it stops working. Okay, and the typical elements that you are going to find in a Hall thruster, which looks like this. This is a brand PPS 1350, okay, which is a very classical Hall thruster, is composed of the following. It has an annular channel with the electric walls. Okay, so this is a 3D sketch, and this is an axial radial view. So this is the channel, which is made out of a dielectric material. Then here at the backplate you have an anode, which is metallic, and a gas injector, which is where you feed the propellant. Then you have here outside a hollow cathode, and both cathode and anode are connected through an electrical circuit, okay, which is represented by this electrical connection over here. And finally, we have a magnetic circuit. Okay, so how does this work? Okay, the neutral gas is injected from this injector. Okay, it gets ionized in the channel of the Hall thruster, and the potential difference between anode and cathode accelerate ions downstream. Okay, electrons are generated at the hollow cathode, and part of them go to neutralize the ion plume, and part of them go inside to neutralize to ionize the neutral gas. Okay, but this wouldn't work if we didn't have the magnetic field. Okay, this magnetic field, which is nearly radial, confine the electron motion so that they have enough residence time that is large enough so that they can effectively ionize our propellant. Okay, so now that we know that we are going to be studying this type of thrusters, we have to understand and characterize the characteristic plasma length and times. Okay, so for a typical Hall thruster, which has a discharge potential of 300 volts and a maximum magnetic field of 200 Gauss, the electron temperature is around 10% of the discharge potential, okay, so around 30 electron volts. We know that the ion temperature is much smaller than the electron temperature, and the plasma density lies within this range, okay? So we can generate this hierarchy of scales, okay, which are going to be present in our problem. With this, we can find the following: that the smallest scales are the debye length and the plasma frequency, the inverse of the plasma frequency. Okay, you see that here the fastest frequency is defined by the electron plasma. Okay, and the smallest length scale is the debye length. We know that in this type of thrusters, the electrons are magnetized while ions are not magnetized. Okay, this is because the Larmor radius of electrons is much smaller than the device size, while the Larmor radius of ions is much larger than the device size. We also know that the plasma is partially ionized, so we have neutrals, ions, and electrons living all together. And these two last things, these are key, okay, and these are going to drive some of the modeling decisions that we take over here. So the first of them is that it is weakly collisional, okay, so this means that the weakly collisionality of the plasma is insufficient to reach a local thermodynamic equilibrium, so in principle we need a kinetic model, okay. So the species velocity distribution function, deviate from the equilibrium Maxwellian, and the standard fluid models present some weaknesses, okay? And another problem that we have over here are the very different scales that we have to represent if we want to simulate all the plasma, okay? Which you can see that in length scales you have here a huge range of scales that are relevant for the problem, and in time scales you also have a huge range of time scales that are in principle relevant to the problem. Okay, so we have said before that due to the weakly collisionality of the plasma, we need a kinetic description. So in principle, we need to resolve the Boltzmann equation. Okay, the Boltzmann equation is this one, which deals with the velocity distribution function. Okay, these are gradients in physical space, and these are gradients in velocity space. Okay, because this velocity distribution function depends on 7 dimensions typically. 1 is time, 3 positions, and 3 velocities. Okay. So there are different alternatives to try to solve this very complex equation. The first of them is try to just resolve this equation, this differential equation, as it is, okay, with a mesh in space and velocity, okay, and try to solve it as it is. And the second one is an approach in which you discretize the velocity distribution function into macroparticles that move in your domain, okay. This is currently more computationally affordable than this one, and this is the methodology that we are going to be using throughout the rest of the presentation. Okay, this methodology is called the particle in cell formulation. Okay, why? Because we have particles that are moving in our mesh, which is made out of cells. Okay? So, in order to resolve our problem, what do we need to do? The first thing is that we have to resolve the electromagnetic fields. Okay? So this electric field and magnetic field that appear in this equation need to be resolved. And for this, we are not taking the full set of Maxwell equations, but we're just taking the electrostatic limit. Okay? This is an assumption, okay, a restriction of the problem. And in the end, the problem that we have to solve turns out to be a Poisson problem, okay, of this type, in which the electric field is basically the gradient of this potential that we obtain from this equation. Then we have to move the particles in our domain, and in order to do that, we use this Boris integration method, which is nothing else than a leapfrog integration, in which we have velocities and positions, which are shifted by delta t halves, okay? Finally, we have to correlate the values at the particles and at the mesh. So we have to, in order to move the particles, we need the electric and magnetic fields at the particle position. So we have to interpolate those values that we have at the mesh to the particle position. And in order to calculate the charge density that we need to solve this equation, we need to do the interpolation of particle positions to the mesh. Okay, so this is part of the algorithm which allows you to communicate one thing to the other. Okay, and finally we are just missing this part of the equation which is over here, which is the collisional operator. Okay, and this is solved with an MCC algorithm. Once we have implemented the code, we have tried to validate it doing it differently. So we have participated in a community effort trying to benchmark different types of particle in cell codes along the community. In this case, we contributed to this paper over here, in which we have a successful comparison between 17 PIC codes, which were independently developed by different institutions throughout the world. Okay, here at UC3M we have two codes. One which is with the code that I developed with Enrique, and another one that Miguel Encinar developed, which is a GPU-based code. Okay. And we have also tried to do an experimental comparison with experimental results, which is a work which is being carried out by Mateo Guaita, okay, which he has been comparing PICASO simulations with experimental results in a plasma plume. Okay, so what are the limitations of this method that we have, that I am presenting you? That it has very stringent numerical constraints. Okay, we are limited to resolve the smallest length scales and time scales of our problem. Okay, and the characteristic size is orders of magnitude much larger than the cell size that we typically use to resolve our problem. Moreover, we have another problem, which is that the different species have very different velocities. Okay, so we have around 1 or 2 orders of magnitude in velocity between ions and neutrals, and between 2 and 3 orders of magnitude between ions and electrons. So the time to convergence, as you know, is determined by the slowest species. So in principle, we have to wait around 1 millisecond, which is a lot for the time step that we are forced to use. Okay, so if we try to do this simulation in a 3D case as it is, you can see that this is completely unfeasible. Okay, it's totally impossible. So what can we do to do this simulation feasible in a reasonable time? The first thing that we can do is code parallelization. Okay, the more threads that you put in the problem, in principle, the faster is going to be your algorithm. Okay. The code that I developed together with Enrique was designed to run in a single workstation with 40 cores. Okay, we decided to decompose our problem in terms of particles because these are the most consuming operations. Okay, you can decide to decompose your problem in terms of the domain. Okay, you can differentiate different parts of the domain and solve them independently. Okay, and do some communication between one another. But as you can see, this process over here has to solve much more, has to do much more operations than this one that only has one particle. So in principle, we decided to just go to this kind of decomposition, which is in principle beneficial because it's better in terms of load balancing. In order to implement this code parallelization, we used OpenMP. But this is clearly not enough to make the code run fast enough. So we have to take further assumptions. And an assumption that we can do is that since our device is axis symmetric, let's take the assumption of axis symmetry. Okay? With this, we keep the axial direction, which is the main direction of the plasma is charged, and the radial direction, which covers the plasma wall interaction problem. Okay, however, we are missing the azimuthal direction, and this is an important direction because we know that there are some instabilities over there. So we have to complement our model with some phenomenological effect, okay, which is this anomalous collisionality. Finally, this is still not enough to make the simulations fast enough, and we have to use other acceleration techniques. The first one, the first decision that we can take is renounce to simulate the neutral dynamics. These are well covered by other models, okay? And here we are focused on resolving correctly the electron and ion dynamics, so we can just drop this thing. Okay, use a very simplified law for the neutrals and try to get a good solution for electrons and ions, okay, which is the most complicated thing. And finally, we can use an artificially increased vacuum permittivity, okay? The two parameters that are limiting our time step and cell size are proportional to the square root of these parameters, so if we make this thing larger, we can in principle increase these two numbers, okay? But bear in mind that with this, we are modifying the physics, okay, to make the simulations possible, okay? So some of the results are going to be affected by this, although we hope it's not affected too much. Okay, so the first test case that I'm going to show you is a simulation in a simplified configuration, okay? And the motivation of this work was just to analyze the wall interaction and how are the functional, to analyze the macroscopic transport equation when the velocity distribution function is non-Maxwellian, okay? We are trying to retain the main elements of a Hall thruster discharge, but keeping it as simple as possible for the analysis, okay? So here you have some simplification, which are basically we are taking a radial magnetic field, so we don't have any curvature. We are dropping cylindrical effects. We are only using a subset of collisions, and we are using an augmented vacuum permittivity to make the simulation run fast. Okay. The main plasma results that we are getting over here are very similar to those that we are used to in Hall thruster discharge. The potential increases a little bit from the anode to this maximum, okay, and then it decreases, accelerating the ions downstream. The electrons that are generated at the cathode, okay, are heated up by Joule effect. Here you have the maximum electron temperature very close to the thruster exit, and then it decreases inside due to ionization, collisions, and losses to the walls. The electron density grows in the Hall thruster channel due to ionization, and then it decreases outside due to plasma acceleration downstream. And finally, we can see that most of the plasma is quasi-neutral. This means that the electrons and ions we have almost the exact same density of electrons and ions in all points in our domain, except very close to the boundaries, okay? This is a very well-known effect, and this small region close to the walls in which we have non-neutral effects is called the device sheath, okay? So this is the expected trends for a Hall thruster. Now, let's analyze in detail what happens inside. So if we calculate the velocity distribution function, which is the thing that is is still under is an interesting thing that, to investigate, we find that first, the radial velocity distribution function is depleted below the wall collection energy. So here, this is the energy to reach the wall from a certain point, okay, and you see that the velocity distribution function follows this line, and here you see a sudden drop of this velocity distribution function. This is due to electrons going to the wall and never getting replenished this part because the collisionality is very low. Okay, if we increase the collisionality, this would go back to the Maxwellian distribution function, which is the equilibrium one for a highly collisional fluid. Then we can also see that the BDF is near the axial BDF is near Maxwellian. Okay, in the axial direction, close to the exit, but it is asymmetric, very close to the anode. Okay, these are electrons that are traveling towards the anode, but they are never coming back because they are collected there. Okay, and this generates this asymmetry in the velocity distribution function. And this also generates a lot of effects in the macroscopic response of electrons that we're going to analyze now. So let's start with the electron momentum equation, okay, which is this one, in which we have a balance between the divergence of the momentum flux tensor, the electric force, the magnetic force and a collisional force. Okay, so this is the full equation, and let's dig a little bit deeper on what this term means. Okay, this is the momentum flux tensor, which is defined as the second order moment of the velocity distribution function, and if you want to write it as we typically do in a fluid approximation, it is composed of two terms: inertia and pressure. Okay, this pressure tensor is in principle full. Okay, and we're going to call the gyrotropic part to the main diagonal part and gyroviscous to the off-diagonal part of the matrix. Okay, this gyroviscous is a bit misleading, okay, because it has nothing to do with viscosity. It's just a name that they have given to these terms, but it has nothing to do with viscosity. For the magnetized electrons, typically we know that this pressure tensor is anisotropic in the gyrotropic part, so these terms are different, okay, and these gyroviscous terms are much smaller than the gyrotropic part, but still are present, okay. What does the classical fluid approximation, drift diffusion fluid approximation do? The first thing that they do is they neglect inertia. They say that the electron mass is very small, so they just drop this term. Then they say that the gyroviscosity, since it is small, we can drop it. So they just drop all the gyroviscous terms. And finally, they say that the anisotropy is small, so they just assume an isotropic pressure. So from this expression that we have over here, you just go back to the classical gradient of pressure that you find in most fluid approximations. Okay? Now, the final Larmor radius effects that are going to appear later on gather basically effects of electron inertia and gyroviscosity, which are the two effects that are not typically considered in most fluid approximations. We can now take the results from our PIC code, okay, and try to build the different terms of this equation. Okay, along the axial and radial direction, we get the classical solution, or something very close to the classical solution, but along the azimuthal direction, we have found some novelties. Okay, why? Because, well, in the azimuthal momentum equation, all the terms are very small, okay, and the final Larmor radius terms, which are this and this, should not be neglected a priori. Okay, because all the other terms are also small in this equation. So this is once again the same equation, and if we drop the final Larmor radius terms and we say that the collisional term is proportional to the current and the collisional frequency, we get to the classical relation, okay, in which the ratio between the azimuthal and axial electron current is given by the Hall parameter. Okay. So if we plot these two things, if we plot the Hall parameter, which is this dashed line, and the effective Hall parameter, which is this the ratio of these two currents, we find that there is a large mismatch near the anode. Okay, so let's try to find out why. Which of these two terms is going to be the one responsible of this? The first term, we can see that this first term, okay, which is this final Larmor radius term, becomes very relevant near the anode, and it is indeed the one responsible of this deviation from the classical behavior. The second one, in principle, has a very small radially average contribution, okay, but if we focus on a given axial section and we plot this momentum equation along the radial direction, we are going to see that this term is the one responsible for some small oscillations in the axial electron current. Okay, this phenomenon is well known, and it is typically referred as near wall conductivity. Okay. Then, of course, if the velocity distribution function changes from Almas-William, we are also going to find some non-standard effects in the electron energy flux equation. Okay, so this is the kinetic description for the energy flux vector, which you can decompose in these components in a fluid formulation. Okay, basically this is the flux of enthalpy, this is the heat flux. This is the flux of inertia, okay, and here you have some contribution that comes from the fact that your pressure tensor is not diagonal and isotropic, okay. So as you can see, the heat flux, the energy flux is very complex, okay, and we find the following: that these two terms that are typically not considered in the drift diffusion electron approximation are in principle small, okay. Here you have these green and these brown lines that are small. And the other two terms that are typically considered in the fluid approximations, they are the ones leading they are the ones that are they are the most important in this equation. But what happens is that typically we model the heat flux as a with a Fourier law, in which basically we say that this heat flux is a conductivity tensor times the gradient of the temperature. And if we plot the Fourier law with respect to the kinetic heat flux, we can see a huge mismatch between the two. Okay, this means that the heat flux that we have in our fluid models is not clearly representing the realistic heat flux that is going to happen in a weakly collisional plasma. Okay. Finally, we're going to talk a little bit about plasma wall interaction magnitudes, and here we are going to define some non-dimensional magnitudes in which we compare the results that we are getting from the practical initial simulation, so the kinetic simulation, with respect to the classical result for Masurian electrons. Okay. So here, this sigma represents the ratio between the electron current with respect to the theoretical electron current, and this parameter theta represents the ratio of the electron impact energy to the wall with respect to the theoretical one. Okay, the result that we get is that in this region, which is close to the exit, these two parameters lie within the ranges that we were expecting from previous 1D radial peak models, okay, which were capturing already these effects. However, if we go close to the anode, we are going to see that these two parameters change dramatically, okay? And one can at least expect this behavior because of the very different behavior of the velocity distribution function at the exit and close to the anode. Okay, so with this, we finish this first analysis, in which we have a very simplified scenario, and we try to move on to a more complex scenario. Okay, basically here what we are doing is including more physics, and we are using a magnetic field topology which is more realistic. Okay, why is the magnetic field topology so important? Because we have seen that in previous 1D model that the magnetic field curvature has a strong effect on the kinetic plasma response. Okay. Furthermore, we are using a magnetic field topology that presents a null magnetic point at the anode, okay? And we are also interested in analyzing this kind of topologies because some of the thrusters use this kind of design, okay? So we are interested to understand what happens over here. The first conclusion that we get from running this simulation is that we basically get the same result as in the simplified scenario. So we confirm the conclusions that we got before. So final armor radius effects are important. Heat flux does not follow a Fourier type law, and the wall interaction magnitudes differ from the classical theory. But what I want to focus now is what happens in the plasma. Upstream and downstream the magnetic separatrix, okay? The magnetic separatrix is this line that I'm plotting here in red, okay? Which passes from the null magnetic point, so the point where the magnetic field is equal to 0, okay? And it's going to distinguish two very different regions of the plasma, okay? Downstream the magnetic separatrix, we have some magnetic field lines that connect the two dielectric walls. They have a mild curvature of the magnetic field. And the results that we are getting in this region are expected from a magnetic lens topology and are aligned with those that were obtained previously in 1D models. But when we analyze what happens here downstream, upstream the magnetic separatrix, in this triangular region over here and over here, we find something different. Okay, we are going to find that the magnetic field is nearly axial. It partially shields the lateral dielectric walls, and we find a very complex response near the anode. So the first thing that we are looking at is at the role of the magnetic separatrix guiding the electrons. Bear in mind that since the electrons are magnetized, they cannot easily cross magnetic field lines. Okay, and this magnetic separatrix, what it's doing is guiding the electron flow towards the anode. This can be seen from the wall magnitudes. For example, here I'm plotting the particle fluxes to this upper wall. Okay, and here you see what are the fluxes at this throughout this surface, and you see a sharp drop. Okay, at the position where the magnetic separatrix intersects the wall. Okay, maybe it is even clearer when we plot the electron current. Okay. in these regions close to the anode, okay, and we can see clearly the channeling effect of the magnetic separatrix in guiding the electron currents toward the anode. So all the current is basically located at the point of the null magnetic point. And well, this is also putting some sharp changes in other plasma properties that I'm not showing here. Furthermore, the lack of electrons reaching this upper dielectric wall generates a collapse sheath, which is basically a region of a material wall which doesn't have where the electric field doesn't go towards the wall, okay, like it happens here, okay. The electric in this device sheath, what happens is that ions are accelerated, electrons are repelled, which is the classical configuration. Here it doesn't happen, okay? And this doesn't happen because we have very few electrons capable to reach this region, and therefore, since the dielectric condition has to be met, so the electron-ion current has to be equal at the wall, we have an electric field which is repelling the ions going to the wall, okay? And well, other unconventional plasma response near the anode is further discussed in the article, okay? So we have seen that this kind of magnetic separatrix and complex magnetic topologies lead to some strange behaviors in the plasma. So the next step in this is we increase the difficulty a little bit more, and we try to analyze what happens in a magnetically shielded Hall thruster, okay? This is, in this kind of thrusters, we use a very complex magnetic field topology, which you have over here. Here, the magnetic separatrix is depicted by this black line, okay, that you have over here. And well, this configuration has shown that it leads to improved performances, it limits the wall erosion and heat loads, and it is very beneficial for modern Hall thruster. However, there are very limited kinetic effects. There are very limited kinetic studies on this type of thrusters, and we try to, what we do now is try to analyze what happens to the electron population in this type of thrusters, okay? The main, when we run this simulation, the first thing that we observe is that we retrieve the classical features of a magnetically shielded Hall thruster, okay? So basically, we have a relatively uniform potential in the Hall thruster channel, and all the acceleration region is pushed downstream. We have a low electron temperature within the channel, and the temperature peak is mainly moved outside. We have a channeling of the electron currents toward the null magnetic point, okay? And that the ion impact energies are below the typical erosion threshold, okay? So this basically confirms some of the experimental evidences that we have over there. But when we analyze the velocity distribution function, we find that it deviates significantly from the Maxwellian, okay? And indeed, it deviates significantly more than in the previous cases that we have analyzed before. It deviates more than in the radial case and in the conventional case. The simulation results suggest that we have two different populations, okay, coexisting together. So here we have, in this main region, we have most of the electrons, which are more or less well described by a Maxwellian distribution at the local value of the electron temperature. But then we also have these high energy electrons, okay, which are a second population, and these are following a completely different trend, okay, and that we need to understand a little bit better and analyze a little bit better. As you can imagine, this is going to affect all the macroscopic behavior of the electrons, okay, and the plasma wall interaction magnitudes, okay. So with this, I have finished basically all the topics that I wanted to cover on plasma wall interaction and the non-Maxwellianity of the electron distribution function, and now I want to cover a little bit fast the anomalous transport, which is the other big problem in Hall thruster, okay? This anomalous transport is named like this because the measured electron current, okay, is much larger than the one that can be estimated only by the action of the classical collisions, okay? This is classically attributed to plasma instabilities, and the main theory right now is that this anomalous electron current is driven by the electron-cyclotron depth instability. So in this work, what we do is we revisit the theory of the instability. We try to design a simple simulation that complies with the assumptions of analytical derivation. we analyze the growth and saturation of the instability, and we attempt to find a relation between the ECDI and the anomalous transport in Hall thrusters. Okay? So here we're only simulating a plasma made of electrons and ions. Okay? We use a realistic vacuum permittivity because the plasma stabilities are very affected by this. Okay, there's ample literature in which says that if you change this number, the plasma response is going to be different. So we are now using the realistic vacuum permittivity, but this forces us to restrict ourselves to small simulation domains and light ions, in this case hydrogen, for this fundamental study. Okay. So the different stages of this instability are the following. So first we have the onset and growth of the instability, in which we have the growth of the oscillations in the plasma. We find that several unstable modes are excited, and the simulation results are more or less aligned with the linear theory. What do I say when I say that are more or less aligned with the linear theory? Is that basically the unstable modes are those where we find resonances in the theoretical dispersal relation. Then we have the transition and saturation region, in which is characterized by these vortex structures in phase space. Okay, these are very characteristic of ion wave trapping. We find that the instability transitions to a different kind of relation. Okay, which in this case is ion acoustic, and at the end of this phase, the plasma oscillations stop growing. Okay. Finally, the last phase of the development of this is that there is a decay and vanishing. So in the end, we have quenching of the plasma oscillations. The vortex structure that we were observing before is blurred, and the plasma reaches a new equilibrium. So in principle, if we plot the anomalous current over time, we see that this doesn't generate any long-term transport that we can measure. Okay, but this gives us an important measurement that is going to be important later, which is the saturation time, which is where we find the maximum anomalous electron current. Okay, so later on we change a little bit our simulation setup, and instead of simulating a fully periodic case, we change the axial boundaries by injection and removal boundaries. This is indeed closer to what a Hall thruster does, because it implies a finite ion residence time, and this ion residence time is calculated like this. Okay, we have this ion residence time is the ratio between the axial length of our domain divided by the axial velocity of ions. Okay, if we do a parametric analysis of the long-term behavior of the anomalous current, we see that in some of the simulations, we are able to drive some electron current. Okay, so here you can see clearly that here we're driving some anomalous electron current. If we compare this with, we use this ratio of the ion residence time and the saturation time, we see that the maximum electron transport is found when these two times are equal, or at least comparable. When the ion residence time is much larger than the saturation time, the instability quenches and the behavior is very similar to the fully periodic case. And if this ion residence time is much smaller than the saturation time for the instability doesn't have enough time to develop. Okay, so basically we don't have any transport because the instability didn't have time to develop. Okay, so this is the main conclusion that we have over here. But how do we can relate this to what happens in real Hall thruster? Unfortunately, we cannot do the full simulation because we are limited in our computational capabilities. So what we try to do is propose a scaling law. Okay, here we challenge our proposed scaling law with respect to some simulations. And well, basically, when we do the numbers for a Hall thruster, it seems that these two numbers match quite well, which means that the electron cyclotron drift instability is, in principle, capable of driving some anomalous current. Okay. Now Guillermo is continuing this work with a more realistic scenario and with a GPU code that he has developed together with Miguel. Okay, and he's now trying to push towards a more realistic scenario and increasing the complexity of the analysis that we have performed so far. Okay, so basically with this I end my presentation. I just want to highlight the main conclusions, which is that the low plasma collisionality in the Hall thruster is insufficient to reach a local thermodynamic equilibrium. Okay, so that the electron velocity distribution function is not Maxwellian. we have a different behavior in the near anode and near exit, and we can also find different behaviors depending on the magnetic field topology that we use. In the macroscopic response of electrons, due to this non-masculinity of the electrons, we find that the final armor radius effects are important, that the heat flux does not follow a Fourier type law, and the wall interaction parameters differ from classical theory. We also saw that the normal sheath can collapse under certain conditions, and we are still investigating what happens in the case of the magnetic shielding Hall thruster, which is still very poorly understood. And the last thing is that we have done the first steps towards the characterization of anomalous electron transport. Okay, we have seen that in principle the ECDA is capable of driving cross-field electron transport in a finite plasma. However, there is still no law relating the plasma conditions with stabilities and transport properties. Okay, so this is still work that lies ahead, and we are continuing the research with the thesis of Guillermo. Okay. Some other studies that we are doing with this particle initial code, which is not restricted to the things that I've shown so far, is a 1D axial model with a reduced model for radial losses, the analysis of the kinetic electron response in grid ion thruster, and trying to do a 3D modeling of plasma by doing a modal decomposition in the azimuthal direction. So in principle, we are moving closer towards a fully 3D description, but keeping the cost still low enough. Okay. Some future work that lies ahead is the analysis of plasma wall transition when ions are also magnetized, which is a scenario that we haven't considered so far. The improvement of the neutral model, and including some electromagnetic effects. Okay? So with this I conclude my presentation, and I'm here to take any questions that you may have.
So we have some time for questions. Who want to start?
Thank you for the talk. It was very interesting, and there was a lot of take-home message for me. And my questions are pretty much fundamentals. Like you talked about macro particles, which includes ions, electrons, and neutral particles. They have different time scales. And typically you go with the lowest time scale to decide your grid size and everything. Do you also have adaptive mesh refinements, like based on the local cell and mean path, you can just increase or decrease?
For now, no. Now it's just a uniform mesh in which we put our particles and we move them around. Okay, we don't have any local mesh refinement. I think that because I think that in DSMC codes they do it very often. Okay, they do mesh refinement wherever you have more particles. You do smaller cells. Okay, because in principle you need to resolve there the mean free path. Okay, better. And in other regions you can make it coarser because you have less particles, so less collisions. Here the cell size is limited by the Debye length, which is a different metric, and it's a bit difficult to define how it's going to behave. But of course, you can do this mesh refinement in a smart way, but it is a complex task. Okay.
Is that the reason to accelerate the simulations? You mentioned about renouncing the neutral particles.
Can you repeat the question?
You mentioned about renouncing the neutral particles, like remove it, just keep the ions and electrons. Like, what does that mean? Does that mean?
So, well, in the plasma, we have 3 different species, which are ions, electrons, and neutrals. Okay, we know that neutrals are much slower than electrons and ions. And for the analysis, we're basically interested on the behavior of electrons. If we have to simulate everything together, the simulations are too costly. So we decided to keep a simple model for the neutrals, which doesn't track the actual dynamics. So we can rule out this time scale from our problem, and we can get convergence in a reasonable time. Okay.
Right.
Of course, if we can at a certain point simulate them in together with the plasma species, it would be perfect. But for now, it's too computationally challenging to put everything together in the same model.
Okay. And also, typically in PIC, you have both fluid models and particle. Like certain particles you consider as particle themselves, and for example, electron can be considered as fluid model as well. So it's a combination of both.
Yes. So these are what are called hybrid models. Okay. And the problem with this is that, as we have seen, the electrons do not follow the classical laws for a fluid.
Yeah,
Okay, so if we are misrepresenting most of the important magnitudes for the electrons. So basically, we are not resolving well the momentum equation. We have uncertainties in the heat flux. The wall interaction parameters are completely different from the theory. So what we are trying to do here is do a more simplified scenario, okay, in which we can analyze all these effects, which are different from the theory, and try to get some conclusions and at least know which effects are differing from the classical theory in order to improve in the end the fluid model, because in the end you don't want to run a peak simulation always, okay? You want a fast model which represents your physics relatively well. So if we can find a way of incorporating this kinetic information into a fluid model, it will be perfect, okay? For the moment, it is very challenging. We haven't found an easy way of putting everything together.
And the probably last question. So the boundaries are also treated as fluid and particles separately based on like whatever you choose. Like for example, for electrons, you choose them as fluid models boundary, and for ions or neutrals, you consider them particle interaction with the wall, like two different boundaries?
Yes. This is what hybrid models do. But we know that these hybrid models rely on a fluid model for electrons, which is wrong.
Yeah. Thank you.
Not wrong, but doesn't include all the physics.
Thank you very much. Yeah, we'll discuss more later.
Okay, thank you, Alberto, for this interesting review of your results. I would be interested in asking you, what would you like to do beyond what you have presented here? No? What are your plans for the midterm?
Well, now that we have this project with the thesis of Leonardo of simulating a thruster that has a wave inside, this is going to include an additional layer of complexity, which is the particle-wave interaction. So maybe going to electromagnetic effects is going to be interesting, because it adds new physics which I haven't analyzed so far. Okay, and it's also a challenging effect. So in this kind of thruster, you're going to have the three problems together. You have the electromagnetic effects plus wall interaction plus anomalous transport in principle. So with this, we have all the complex things all together.
A very complete problem.
Yes.
Okay, thank you.
Thank you, Mario. More questions?
Hi, Alberto. So I was wondering, I understand that your research is about the basic or fundamental properties of plasmas, but I was wondering how representative is of the actual performance of a half thruster your 2D approximation.
Okay, so this approximation, the problem with this approximation is that we rely on this phenomenological model for anomalous transport, okay? So we have to include this because we are restricted to 2D, okay? This, we know that it affects a lot the actual performance of the thruster. So in principle, yes, if you wanted to represent faithfully without any information from outside the physics of a whole thruster, you have to resolve a full 3D problem, okay? Or at least resolve it consistently a little bit of the azimuthal direction, which is why we also started working on this modal decomposition along the azimuthal direction, because it's a way of including some azimuthal information without having to resolve the full 3D problem. Okay, so we hope that this allows us to get a little bit better results without having to rely in these numbers, which are just phenomenological law, which I can put whatever I want because it's something I don't know.
So I don't know much about the plasmas, but those numbers look to me like a turbulent model. So it's the kind of the part of the things that happen in 3D that you don't see when you are looking in 2D.
Yes.
But I was also wondering about the fact that the cathode is in the plots that you have or the figures you have shown, the cathode is something that is located at a particular azimuthal location, and that is going to change the way electrons move at different planes, right?
Yes, this can be, in principle, can lead to a can lead to changes, because it's not the same having a localized source of electrons and having a ring, basically, of electrons, which is something that now Mateo is studying for a different configuration. And indeed, in the review, he got some questions about this thing. It is true, but for the moment, it is the best thing that we can do. The good thing is that in this kind of thrusters, okay, the plasma gets uniform very soon. Okay, so it's just at the cathode. It is true that it behaves as a source, but as a point, okay, of a blob of plasma, but then it becomes very uniform azimutally very soon. Okay, so we can say, okay, we commit a mistake, but we hope this is not very big.
Okay, and then the 2D simulations that you are doing are representative of the part that is expected to be more or less uniform, or is representative of the cathode because you have the input of electrons?
Well, in principle, if you move a little bit away from the cathode, everything is going to become more or less uniform. So it wouldn't matter too much in which plane you are. Okay, so it's just going to be a matter of the precise physics that happens very close to the cathode, where it's going to matter whether you model it as a point source of a ring. But if you move a little bit away from this cathode, the plasma gets very uniform. Okay, and I expect that there is going to be no important change due to this approximation.
Okay, thank you very much.
More questions? I have a couple of them. One is that I think that you have behaving more like a physicist than an engineer when you have said that the fluid model is wrong. Okay. When we use the hyphen code, that is a hybrid code, and several theses has been working with hyphen, they are able to reproduce. It's an axial radial code as yours. They are able to reproduce the behavior of the plasma discharge. They are able to, with some empirical model for these turbulent effects about the anomalous transport that will need to be fit with some experimental data. But they explain many of the things that are happening there, and they obtain with profiles, etc. And well, mainly they explain how the thruster behaves. So, is so important all that the fluid model is missing? This is one part of the question. And the second, if with PICASO you want to do the same type of simulation at hyphen, how long does it will take you?
Well, the importance of the things that fluid models are missing, it depends on what you want to study, as always. Okay, but okay, I think that we have found important things that do not behave as we expected it. So, for example, the wall interaction parameters, I expect that are going to have a big impact on the plasma behavior. Indeed, some of the people doing experiments have reported that basically they cannot match the experimental temperatures that they get from different techniques if they don't, in hybrid model, if they don't change the energy of electron reaching the wall. So this can be due to this behavior that we obtain over here, this value of theta, okay, which is differing from 1. And I think that some experiments are pointing in the direction that this is a thing that it's going to be important if we want to replicate faithfully electron temperatures. Okay. Also, the heat flux, I think, is going to be an important thing to model. For the aeroviscosity, I'm not so sure how important this is going to be. For this, I will have to think a little bit more in detail. Okay. And the second question was about
how long does it will take PICASO?
How long?
Years.
How long is the simulation that you want to replicate, Eduardo?
The one that hyphen, the one that
1 millisecond?
Yes.
Probably 2 orders of magnitude more than now. And now a simulation can take several weeks, so... Okay.
Possibly we cannot wait for you.
Either we improve a lot the parallelization and the algorithms of the code, or with our current knowledge, we cannot do it. Okay, another alternative is that if we manage to make codes that do not resolve these small scales work and work fast, maybe we can cut down these simulation times. But these models also have some problems, okay? Because there is no free lunch. In the end, each iteration is more costly because it's more difficult to compute the different times that you need. So it is not clear to know if there's going to be a clear advantage of one with respect to another, okay?
Okay, so one important goal is that with this kinetic simulation, you can provide answers that can improve the fluid model.
Yes.
If you want to still
of course.
simulate the thruster. You have to, this is my last question. You have talked about the heat flux, the issue of the model of the heat flux. Next week will be with us in a seminar here, Alejandro Álvarez Laguna. He's part of the committee of the thesis of David De Poli, but he will give a talk at 12:30. Okay. And Alejandro, is proposing an alternative to your line of research. That is, let's forget about the kinetic simulation and let's go totally fluid, but with fluid equations that not rely in the typical 5-moment fluid equation, typical of
you go to higher orders.
Fluid mechanics, and to go to 14 moments fluid equation, where some of these aspects can be reproduced in these high order moments. What do you feel about this alternative?
It depends on how high you have to go with moments. Okay, if you have to solve many equations, at a certain point it will stop making sense to resolve the fluid equations, and it's going to be cheaper to run the fully kinetic simulation, because, as you know, the fluid hierarchy of equations is not closed, so you have to decide where to close. If you we are closing in the heat flux. You can close in the next moment or in the following. The more moments that you keep in your formulation, the better the approximation is going to be. But where do we stop? This is the important question that one has to ask himself. Okay, because in principle you can continue forever.
Is there ever a guarantee that you can truncate this if you go far enough? You will get good results
At infinity.
Well, I understand that this is part of the research of Alejandro. Alejandro has an ERC starting grad to study this problem. Okay, how many moments you need to add, and which are the improvements you get with the moments. Okay, but this is an alternative. We'll know more about this next week. Okay, thank you very much, Alberto.
Thank you.